Welcome. In this presentation, I will explain what Ceph Telemetry is, why it is useful to you as a user of Ceph, and why you should enable it. My name is Marowsky-Brée. I work as the architect for software-defined storage at SUSE, and thank you for your time today. Reviewing our agenda, we will talk first about the goals and motivation behind providing Ceph Telemetry features. I will talk briefly about the data collection methodology and the method I use to provide this analysis and how it relates to the upstream efforts. Scope and limitations are really important, so we have context on what kind of conclusions we can draw from this data and which we shouldn't. And then finally, why you're all here, the pretty pictures and a peek at the data that we have already assembled and conclusions that we have seen. And in the end, again, we'll review how to do Q&A in this kind of format. Our goals and motivation as a development community are quite straightforward. We want to make better product and project decisions in the interest of our users and those that deploy and use Ceph. And to do that, we need to understand actual deployments in the field. We also want to be able to detect anomalies and trends proactively before they escalate to the point of being reported as bugs. So, say, being able to see the impact on average cluster performance of a new deployed version. So, telemetry will not replace but augment our support channels. Support cases tend to be only opened once an issue has been noticed by a human being. And also when we want to do analysis, the support incidents obviously then are from systems that are unhealthy. So we rarely get a lot of data from systems that are healthy, which affect our deployment and development strategy. We also want, as I've mentioned, to identify issues before they escalate, so we can proactively fix them before our users have to take personal action. And also, when a support incident is reported, sometimes we have to prioritize. So we need to understand how representative is a support case of our actual user base. And to do that, we also need to be in a better position to understand, again, actual deployments through telemetry. So from a user and customer point of view, we want to improve our project decisions to reflect your particular usage, to make sure developers and other partners understand your deployments, and again, detect those anomalies and trends before they affect you personally. And again, we have other channels of soliciting feedback from our users. The Ceph community also runs an annual survey. But surveys are limited in scope and depth. We can't ask all these detailed questions because then the survey would take forever to answer. So surveys still provide valuable feedback, namely like on priorities, on what users actually care about, and where they think their priorities are in areas that are not so easily quantified, such as documentation. But telemetry, on the other hand, just allows us to get way more details and more frequent updates. We can't run a user survey every week and see how trends have changed. And at the same point in time, and surveys are also filled out by humans, which means there are typos, units aren't always consistent, numbers are mixed up, all these things. So telemetry obviously removes these kind of issues since they're automatically reported. So to conclude, telemetry and surveys both have their place and provide also valuable options for cross-checking one against the other. So having mentioned the survey, this is a good time to take a sneak peek at the survey results from last year. A more detailed analysis will be upcoming. So we had 404 responses. Yes, 404. The total capacity reported was on the order of almost 1.2 exabytes, which is really amazing, but again uncertain, since when I reviewed the feedback, not all units were consistent. So there's a certain amount of uncertainty around these numbers. And 33% said they had already enabled telemetry functionality, which I really love, and it's a great result at this point in time, since telemetry is fairly new. We'll look later at how these numbers match up to the amount of telemetry reports we actually see. But that also means that about 2/3 of our user base has responded to not having enabled telemetry features. And why have they not enabled telemetry? So 84 responses actually said, well, we weren't aware this feature existed. So I'm hoping that this presentation and the blog will help overcome this. 74 said, we really want to understand the data privacy behind these reports better, which I will also address in this presentation. 54 reported that they are running a Ceph version which do not yet support telemetry. That's obviously a tricky thing because we can only backport so much functionality to older releases, but we'll also take this into account going forward. And 33 responded that they are in firewalled or air-gapped environments, meaning they don't actually have the ability to establish a TCP connection to our telemetry server and have those reports sent. And that's also a feature that we'll look at in the future. So how is telemetry implemented in Ceph? There's a manager module that aggregates statistics from the cluster. This anonymizes the dataset, no IP addresses, no host names, no pool names, no RBD names. None of these identifiers are included. And these aggregate statistics are then relayed securely via an HTTPS connection to a telemetry endpoint hosted by the Ceph Foundation. So this is not an initiative by any downstream vendor, but it's a data corpus that benefits from getting as much data into it as possible. So it's also an upstream first initiative by the Ceph Foundation, which hosts the server. The data is licensed under the Community Data License Agreement sharing version 1.0, which could at a very high level think of as the data set equivalent to a GPL license. I would encourage you to read the actual license, but that's why we've chosen it and what it boils down to, because we believe that sharing this data improves the outcomes. And also it is opt-in. It is not enabled by default. You have to turn it on via the command Ceph Telemetry on your cluster. We encourage you to do that. But again, we are not at this point enabling it by default. So we are taking a number of precautions to ensure that the data remains private, that we build a significant amount of trust with our users, and that we prove ourselves worthy of it. Moving on, reviewing the versions of Ceph that do support telemetry. This was first introduced in Ceph Mimic. There was a number of significant improvements in Nautilus and now obviously in Octopus. It was backported to Luminous, and that version is still being reviewed. And it's also supported in all current commercial releases. So at this point, if you're running a production Ceph cluster, we would hope that you're in a good position to be able to enable this functionality. How can you actually see and get a better understanding of all the data that is shared? There are so many data points, I cannot review all of them here. Data is divided into 3 different channels. There's a basic data set, which will be the primary focus of this presentation. There's also data that is shared about crashes your cluster has encountered, which is obviously really important for developer metrics, and also device metrics such as device health, smart data, which is a third channel, and that is not part of this presentation. You can take a look at all the data your cluster would report using the Ceph Telemetry show command. Here we are going to be looking at total aggregates for capacity and usage, all the data that is available about OSDs, MONs, hosts and their versions, and some of the other data that we have available, like erasure coded profiles and so on. So that's part of the basic package, and that's really what I would encourage you to use, because that is where we see the most value to understanding what kind of features your system uses. The crashes and device matrix are also very, very important to us. So Obviously, that was a very fast run through the high-level details of the Ceph telemetry data, but we all want to get to the actual analysis and pretty pictures. Before we can do that, though, we need to take a look at the limitations of this work. So first, the biggest concern, this is a biased sample, since many clusters in the field will run older versions that don't yet report telemetry data. It's something that users have to actively enable, which means that systems that just get deployed and never touched will not be represented. The environments need to have access to be able to upload this data, which is a concern for systems that are mission critical environments and that may not have any sort of external internet connection at all. And again, enterprise users are more conservative about the versions they deploy as well as the features they enable. So again, these will be underrepresented. So this is not representative of all deployments of Ceph. So it has to be treated with the utmost care in what kind of conclusions that we draw from this. This is not a representative sample. But we can take a look at trends if we don't assume that all the numbers are exact. Okay, so there are some conclusions that we can draw as long as we keep those limitations in mind. So in the Ceph community, there's also an ongoing effort to have an upstream community dashboard that is actually updated live. What I did for my analysis here, because I was bored and had a week to spare, I wanted to take a look at Python and pandas and that kind of data analysis tools. So here I accessed the whole data corpus, ran a small script that cleaned it all up, flattened it into a table, resample it to a common interval, because obviously not all clusters report at exactly the same time or even at the same intervals. Like some report daily, others report every third day, every other day, all sorts of mixes. So and then I took a look at the resulting dataset, found errors in my version of flattening and filling that data, and also found errors in the dataset that I had to then fix with a re-import. So this is all basically, exploratory data analysis, probably not even 101, but like college grade, because I'm not really a data scientist. But this was all also very useful for me to understand on what kind of dashboards we should have upstream, and what kind of issues we have to overcome there. So in conclusion, pandas is absolutely amazing and you all should go play with it if you can. Okay, and with that overly simplified, way too fast run through so I don't lose your attention through what telemetry is, let's take a look at those pretty pictures and the first analysis. So we'll look at overall trends in the system. We'll look at an example of finding an actual bug. We'll take a look at version and feature adoption so we can, get a glimpse of how our versions are being used in the field. We'll take a look at how we can identify common practices from this data set. And also we'll take a look at how Ceph clusters are sized in the real world. Not how we recommend they are being sized, but what the telemetry data set shows customers and users are actually doing. So the first and most obvious and supposedly simplest question, how many clusters have telemetry enabled and how many clusters are reporting telemetry data? Turns out that this question is not as straightforward because not all clusters report at the same time or even at the same frequency. And there may always be minor issues that prevent a cluster report from being sent in. So what you're seeing here is an interpolation of data points resampled to a daily basis. So if a cluster is set to report every other day, then that day in between will actually be filled with the last known state for that cluster. There's also the question of at which point do we assume that a cluster has gone away. So in this example here, for my analysis, I forward filled clusters for a maximum of 7 days. So if we haven't heard from a cluster for 7 days, we drop it out from this data set, right? And unfortunately, that brings us to the last point on this slide already. In the beginning of March, there was a brief point with the Ceph Telemetry endpoint and clusters were unable to report telemetry data and would actually show a health warning, health error on their cluster. So even though that was harmless beyond that state, it's not a very nice state for your cluster to be in. So many users have chosen to disable telemetry reporting for the time being. And so they have dropped off at the end. And we can already see an uptick as they get around to re-enabling telemetry data. So that's good. And yes, we're going to see that drop at the beginning of March in every future slide that we are going to be discussing. So I will not talk about it on every single slide. It's a valuable lesson for us as a development team to learn, and a situation that we will desperately try to avoid going forward. The next question always asked is, how big is your cluster? How much capacity is deployed with Ceph? Now, again, this is only a limited set of clusters that are reporting, but we can see that before that unfortunate incident in March, we had about 125, 130 petabyte of total capacity, of which around 40 petabyte were actively used. So again, this takes all the redundancy, all the replication, erasure code overheads, and so on into account. So this is a gross capacity in the cluster. Let's cross-check those numbers with the results from the annual survey. I imported the response set to the community survey into my pandas environment as well. And I'm just looking at the respondents that said, is telemetry in your cluster? Yes. So the total capacity of all those clusters comes out to 280 petabytes. And at the same time, this represents or would represent 308 clusters. As we can tell, these numbers are significantly higher than any of the peaks we have seen in the telemetry dataset. So we know you're out there, and we appreciate that you think you have enabled telemetry, but please double check and actually enable it in your environment. As developers, however, the question that is even more relevant than the total capacity deployed is which versions of our software are being run in the field. And here we can see the trend of the numbers over time for the major Ceph versions. So Luminous, Mimic, Nautilus, and finally Octopus. What we can see and what is to be expected is that the vast majority of our clusters in the field run version 14, which is obviously Nautilus, which is the current stable release. We see a very brief use of Octopus already. Those are all the development clusters, I would say, and some systems are running Mimic, but for now I'm focusing on the Nautilus release. So with version 14, Nautilus being the most commonly deployed major version in the field, let's take a look at the minor version breakdown of that release. This chart counts the total number of OSDs on any given version at a point in time. And we can see, as expected, that new versions are being deployed as they are released, and also the total variation coming from clusters joining and dropping out of telemetry reporting. However, what we can also take a look at is how old versions fade out, mostly by being upgraded to a newer release. And this is interesting because while that is happening, we can also see that it's quite rare for an old version to completely fade. In particular, take a look at version 14.2.4.1. That is essentially a hotfix release in response to a security bug that sensibly was deployed with some urgency in early December 2019, but that to the end of this graph has not fully disappeared, even though we are now at much more recent versions. And that means that out there, many clusters are still affected by versions that have long been superseded. And with that, let's take a look at exactly that. How many clusters are still affected by any given version? That means they're running at least one node at that minor version. And this is even worse, right? you can see that there is still a significant number of clusters running 14.2.1 or 14.2.2 and essentially are not being upgraded at all. So clearly a key part of our future research and investigation work will have to center around why our users are reluctant to upgrade and how we can make this a smoother experience for them. And now for a somewhat more quirky analysis. On which day of the week do people install updates? This could be interesting for planning staffing for support, escalations, even when we release updates as a project, or just plainly validates the anecdote that system administrators install updates on the weekend. To compute this, simply take the rate of change for each version day to day, then aggregate all those absolute values so they don't cancel each other out for every given day, and then group by day of week and aggregate again as a simple sum. And we arrive at the following picture. We can see a spike on Mondays and Tuesdays and a spike on Fridays and a minor increase still on Saturday, with almost no change on Wednesday and Sunday. What does this mean? Since most clusters report daily or even at larger intervals, we are going to see some version changes occur on the very same day because they're reported before the cluster reported in on that day, most likely on the day after, and a little bit 2 days later if anyone has configured their cluster to report only on a 72-hour interval. So we would be more likely to see some changes on the day the versions are applied and most of them the day after. So if we take a look at this, it seems pretty evident that most of those updates are applied on Monday with a slight fall off on Tuesday. So in the beginning of the week, people apply changes, and on the end of the week, on Friday, before they depart for the weekend. It seems unlikely that a lot of change happens on Wednesdays or on Sundays because we would have otherwise picked up at least a little bit of change on those very days. So pretty neat, we can tell on which days people are updating their clusters, but to get even better data, keeping in mind the sampling requirements, we would have to go to at least 12-hour intervals or even shorter, which is unlikely. And now for a story some of you may have been familiar with if you follow our Ceph.com blog frequently. One of the eternal questions in every Ceph cluster before the autoscaler came along was, how many placement groups should I have per pool? Right? This is really important for ensuring that data in your cluster is evenly balanced. There's a rule of thumb that you should have 100 PGs per OSD. The actual formula is slightly more complicated, and then it should be rounded to a power of 2. So what do users actually configure in practice? And here we have the top 20 pgdum values chosen across all pools of clusters that are reporting. We see the most likely candidates, namely powers of 2, that is wonderful, but we also see some really odd numbers. 100 is not a power of 2, 192 is not a power of 2, 96 is not a power of 2, 60 definitely not, 12, right? And the -1 at the bottom are all the other numbers combined, so these are numbers that are not on this slide. Okay, let's ask that question differently. How many pools do have a power of 2 pgnum or not? And this graph shows the number of pools where the pgnum is a power of 2 or not a power of 2. Most pools are correctly configured with a pgnum that is a power of 2, but there's also a consistent set at the bottom of this chart where you can see that some are not. And there's really no reason why pgnum should technically be not a power of 2, right? The algorithm that schedules data in your cluster really wants pgnum to be a power of 2. The exact explanation is a little bit beyond this presentation, but how did that happen? Now, we went back and found that some people actually overemphasized that there should be 100 PGs per OSD and then arrived at a conclusion that was not a power of 2. And we also found a documentation example that actually had pgnum equals 100 as an example. So that's what people just copied without reading the rest of the context. So what did we do to address this issue? First, we improved the documentation. We removed the bad example and clarified the impact, improved the UI user experience, so the dashboard and all the tools will now warn. And also if a pool has a pgnum that is not a power of 2, you will now get a health warn state. And most importantly, the PG autoscaler module for the manager was introduced that fully automates the setting of pgnum for a pool. So if you enable this, your cluster should theoretically never have an incorrect value. Right? You can set this to either 1 and it will tell you that something is wrong in your cluster and that pgnum should be changed, or you can set it to fully automated on mode and will manage this setting for you entirely, taking away one tunable that is hard to explain and automating it completely. For the full story of how we first looked at this data, take a look at the URL reference on the slide. And now with the PG autoscaler available, let's take a look how things look today. So the first thing we have to look at is how many clusters out there have actually enabled the PG autoscaler functionality. That was not always reported by the telemetry dataset, so I've cut off the past from this slide because there was no point in showing the slide before that data was reported. And then we can slowly see clusters coming in, reporting the state for this functionality. And at the same point in time, we can also see it being adopted. Some users have chosen to disable it. Most seem to be running it in warning mode at least, so they would get an automated notification that they should readdress that pgnum setting for a given pool, but some have also chosen to set it to on and automate this step entirely. Great news. And then with that, how many pools have an incorrect pgnum setting if PG autoscaler is enabled? As we can see on this slide, the answer is 0, which is excellent news. Mission accomplished, nothing more to see here, moving on. Right? This is probably the best possible outcome. Explaining tunables is great. Taking tunables away and doing the right thing automatically is even better. And that's the kind of data and insight that telemetry data enables. Because no developer would ever have set pgnum to a non-power of 2 value. This was not an error that we would have thought of, but an error that was pretty apparent once you took a look at the available data. That was a direct example of how being able to analyze how clusters are deployed in the real world helps us improve the project and the documentation and the code. But the data that we can see also allows us to prioritize our efforts better. How are features actually deployed? How significant would a bug in a specific area be? This allows us to focus quality assurance, improve support incident assessment, and also hopefully allow us to see why users are holding out on features that we consider legacy. That's really important because sometimes we would like to de-emphasize, deprecate functionality because something better is available, but to be able to do this reliably, we need to understand whether there is still a significant base of users using a deprecated feature. For example, Ceph OSDs support different kinds of backends for storing data on devices, and originally Ceph only supported file store very well, and in more recent versions introduced BlueStore. Supporting multiple storage backends is difficult, and the development team would really like to be able to deprecate file store in favor of BlueStore everywhere. Would that be something that we can do without inconveniencing any significant number of users? The telemetry data says yes. The vast majority of all deployments out there is already on BlueStore. And if you're still on FileStore, we would really like to hear from you. Why? Because you really should be converting to BlueStore at this point, because this functionality is likely to be deprecated in the future. Another question. How many pools are configured with erasure coding versus replication for data protection? If you just look at the number of pools, the vast majority is actually replicated. Only a low but steady portion of pools use erasure coding. Does this mean that erasure coding is less relevant? Let's ask the question a little bit differently. How many clusters are affected by erasure coding? And here we can see that the proportions suddenly change significantly. Even though the majority of pools use replication, about 1 in 4 clusters has at least one pool that is erasure coded. So again, this is a really relevant distinction. How many pools or how many OSDs are affected by something versus how many actual deployments are affected by something. And here we can see that erasure coding is obviously a very widely used feature that is very relevant to our quality assurance methods. Sometimes telemetry just confirms what you already knew. For erasure coded pools, Ceph supports different algorithms how those erasure codes can be computed. Which of those plugins get used in the real world? Again, this is a data point that has not been transmitted by telemetry always, so this is again a shortened graph. And here we can see that the vast majority of all deployments use JRazor, which is the most simple, most straightforward plugin to use. A few of them use ISA, which is the Intel accelerated system. And we already see actually some significant adoption, given how it's a new feature, of the Clay plugin, which is great news as well. Similar to understanding which PG_num values are chosen, for erasure-coded profiles it's very interesting for us to understand which K+M values are used, because there's no way how we could compute and test and benchmark all possible K+M combinations. So understanding what is deployed in the field is really quite helpful. When we now look at that over time, we see that the vast majority are using 4+2, which is a very sensible choice. It has about the same availability profile as 3-way replication, while only requiring a 50% overhead. So good choice. We also see, however, some values that are slightly strange. I will let you look at the screen for a moment, or maybe pause the video to see if you can spot them. Yes, I'm talking about the 2+1 and also those where k is not a power of 2. To just refresh this really quickly, erasure coding K+M means we divide the incoming data into k data chunks, compute an additional m parity chunks for availability and redundancy, and so that means that those additional m chunks are the overhead. We end up with a right amplification m divided by k. So larger k values tend to be more space efficient, and larger m values improve durability, availability, and reliability of the cluster. At the same point in time, K+M in total affect the number of chunks that we need if we have to reconstruct data, at least for JRazor, which is the most common data set algorithm. So it's generally useful that the incoming data blocks can be divided through k for maximum space efficiency. Most software tries to write data in power of 2 blocks, so typically k being a power of 2 as well would be useful. So the question deserves to be asked, are those K+M values what users choose? Or do we need to improve our documentation? We can't really tell at this point why users choose these values. For example, m equals 1 could be fine for a lab cluster where you don't care for data availability, but it would be a really bad choice for a production cluster because you have very little redundancy. Unfortunately, at this point, the telemetry data does not allow us to tell whether it's a production or lab cluster, and that's a flag that we'll introduce at a later date. Ceph Telemetry also tracks which configuration options users have set. It does not track what values they have been set to, because, for example, we track that they have set a password, and obviously we do not want to keep track of the passwords that users set. Still, understanding which options users have configured in their environment helps us understand which values may be more prominent in your user interfaces, which we need to document better, and so on. And for some, there are interesting correlations. For example, we can tell that more systems have configured a public network than they have configured a cluster network. So we can have an idea of what proportion of our systems, for example, have configured a dedicated OSD backend network. It would certainly be interesting to better understand what kind of conclusions and insights we can draw from this kind of data for our user experience going forward. Let's look at real-world sizing now. Can we deduce some best current practices from this data for hardware configuration? And I think that yes, we can. Since we only have a very limited data set, we cannot yet identify trends in data according to the market as, say, hard drives change in price and capacity. But we can definitely tell that there are some trends in the hardware already today in how systems are configured. So this brings us to this table. How to read this? So for all parameters that I've looked at, I've analyzed both the whole population, so all clusters, as well as clusters below 1 petabyte and above 1 petabyte. So that 1 petabyte boundary is arbitrary. It's just what I use to distinguish between a small cluster and a bigger cluster. And then on the right side, we have a standard quartile distribution. So the first 25% go up to that value, up to 50% stay within that value, 75%, and finally 100%. So 100% includes obviously the whole population. What kind of information can we gain from this slide? Well, for example, we can tell that our median cluster has 68 terabyte, which is not very large. So we can assume that there's a significant proportion of lab clusters in this data set. However, when we look at the clusters that are already larger than 1 petabyte, which is unlikely to be a lab cluster unless you're CERN, the median cluster already has 3.1 petabytes worth of data. And the largest clusters that report here go up to 15 petabyte, which is significant. We can also look at the device choices in the dataset for small clusters versus large clusters, so the terabyte per OSD. Here, for example, we can tell that clusters below 1 petabyte actually have hard drives that are 16 terabytes in capacity. Clusters above 1 petabyte don't. Why? Because 16 terabyte drives, while out there, are not the most cost-effective ones yet. At the same point in time, we can tell if we look at the terabyte per host for clusters below 1 petabyte and above 1 petabyte, that the density of nodes increases significantly. So the largest node, so that 100% figure for clusters below 1 petabyte is 230 terabytes. If we compare this to the largest node above 1 petabyte, where we have 628 terabyte per node, we can see that obviously larger clusters are much denser. So it's this kind of information that we can use to understand the size distribution of our clusters, of OSD devices and so on in the real world, and better understand what we should plan our lab clusters for. It would be very interesting if this data also included what kind of network bandwidth these nodes have, but unfortunately that is not currently available in the dataset. Let's close with looking at data that is a little bit easier to digest. OSDs do keep track of whether they are run on rotational media, that means traditional hard drives with spinning rust, versus all things flash. And understanding this markup is very interesting for us from a tuning perspective. Which defaults make sense, and in particular, what kind of hardware should we buy in our lab to represent a typical end-user deployment. So when we look at the entire cluster population, we see that there is a sizable proportion of flash, but the majority of data is still on hard drives. This effect becomes even more pronounced when we then look at clusters above 1 petabyte. So above 1 petabyte, I would go as far as saying that flash use so far is still minuscule. So from this perspective, I would argue that most clusters out there are capacity-oriented archive systems, or that have enough bandwidth and IOPS simply through scale, right? So clearly, hard drives still rule the data center. What kind of future enhancements have we planned? As we've seen, some users have reported that they can't use telemetry because they're in air-gapped environments, and we would obviously love to enable that and make telemetry accessible to everyone. One possible method could be an email transport for telemetry data, or possibly other offline use cases where the data is funneled through the same channels that are used for shipping updates to these systems and then retroactively incorporating their system into the telemetry data corpus. And of course, going through this data, we have found a lot more metrics that we would like. So performance metrics, say average OSD commit latency, these kinds of things. The variance of the data distribution across OSD, so we can tell how effective we are at pseudo-randomly distributing data correctly. What also would be very interesting are client versions, so that we can tell what features are used. We can tell what the minimum client version is that a cluster still supports, but we don't know what kind of clients actually connect to such a cluster, which would be really important from understanding what kind of compatibility testing matters. And while that data is already being gathered on device and fault data, and also crashes that are being reported, I have not included this, and there's also an ongoing effort to perform better analysis of these data pools. And while it was clearly a lot of fun for myself to dig into this data set and play with pandas and Python and matplotlib and all those lovely things for data analysis, what we really want and what Jurt is working on hard are automated dashboards on the Ceph website. That should come really, really soon now. So you can take a look at this data set whenever you want, easily yourself. And once telemetry data has proven itself to be useful and gained acceptance with our user community, we would like to review if there's a basic set of telemetry data points that we can report by default. Of course, there would always be the option to opt out even before the first data has been shared with the telemetry server. But the larger the telemetry data corpus is, the more useful it is for everyone. And with that, congratulations, we've made it to the end. In a real-life presentation, this would be the point where I'm taking questions and would try to answer them. Since this is unfortunately not possible, I've listed many ways how you can contact the project or myself. So I would recommend you go to the Ceph community website, subscribe to our mailing list, join us on our ISC channels. Feel free to reach out by mail directly to myself at lmb@suse.com. Ping me on Twitter, reach out to me via LinkedIn. It's all good. I will try my best to answer any questions. I would like to conclude with encouraging you to type Ceph Telemetry on your clusters so that we can serve you better. Thank you very much for your time.